cut for capacity, locating, weighting, and related problems. Ruslan, the floor is yours.
Yeah, thank you, Zachary. So I would like to thank organizers to inviting me to give, to have opportunity to give the talk. So this is a joint work with Rida Majoub from Université Paris Dauphine and his former PhD student Pedro Liguori, and also my former PhD student Guillaume Marques, and also my long-term collaborator from Universidade Federal Fluminense in Brazil, Eduardo Ochoa. So I start with presenting you the main problem we are working with. So this is a capacitated location routing problem. So here we have a set of potential depot locations, and depots are capacitated, and we have for them the opening costs. So if we open a depot, then we should pay cost. We have also a set of customers with different demands, and we have edges between customers and the depots. And so there are no edges between depots. And we have a transportation cost for every edge in this graph. And we dispose an unlimited set of vehicles of capacity, of a certain capacity, which we denote as Q. So we need to decide first, so there are two types of decision. There is a location decision or opening decisions. So which depot to open. And once the subset of depots is opened, we need to assign every client to an open depot. So this is a classic. This corresponds to the classic location decision. And we have also, the client should be assigned subject to depot capacity. And then additionally, in contrast to the standard location problem, we also need to partition the clients assigned to the same depot into subsets, and each subset should be served by a vehicle also of a limited capacity. And so we need to minimize the both location costs or depot opening costs and the transportation costs. So here I give you the illustration of the problem. So here we have a set of potential depots which are red, and set of clients which are black. So, and this would be a feasible solution. So we open 3 depots from the 5 potential ones, and we assign clients to the open depots, and furthermore we partition the assigned clients into the routes, and we need to minimize the both routing and the opening costs. So why we would like to work on this problem? So first of all, what is interesting here is that this problem is actually a combination of 2 central operation research problems, namely the capacitated location problem, more discrete capacitated location, and the capacitated vehicle routing problem. And so we would like to efficiently solve this problem to optimality, and as it is a combination of 2 central problems, so any advance in this direction would potentially help a lot of other problems, because there are a lot of generalization of these basic problems, and for example there are more than 3,000 papers which has both location and routing in the title. Of course, many of them do not consider the classic problem, but if we can solve the classic problem better, probably we can also solve many other problems better too. So as you can see, the literature on this problem is extensive, and here I give only some references on the standard capacitated location routing problem. And this is of course biased, and also this is not a complete literature review, of course. So in Bellinger et al. 2011, they gave an important set of valid inequalities, which we will also use, and a good branching cut algorithm. In the same year, Baldacci et al. They proposed a column generation based algorithm, actually, it's not a branching price, because what they do is that they first enumerate the set of potentially good combinations of the subsets of open depots, and for each such subset they solve the vehicle routing problem already with the fixed depots. And a similar approach was proposed by Contard in 2014, and it's currently the state-of-the-art approach. So, but as you can see that as we here enumerate the subset of potential depots, this approach does not scale well for the case when the number of potential depots is large. And so, although these algorithms are good and state-of-the-art, they will not potentially scale for the instances with a large number of potential depots. So recently there was these two works about the heuristics, and so now there are quite efficient heuristics for this problem, and also one of the aim to better solve this problem exactly is to be able to estimate whether the current state of the art heuristics are good or not that good. And also I give the reference to the latest survey on the problem. Here, what we want to exploit here, so we want to solve this problem better to optimality, and of course, we want to use all the advances on the classic vehicle routing problems. For that, we will use the solver we recently proposed for vehicle routing problems. So it's a generic branch cut and price solver. So which you can download and use on this website, but only using the solver would not be enough because as I say that it's not only vehicle routing, it's also a location problem, and thus we would need to use additional families of valid cutting planes in order to obtain really good results. And so we will here in this work we use several families of valid inequalities, and I decided to start with a family of valid inequalities which are novel in this work, because I'm not sure I will have time to present all inequalities we use, and so I prefer to start with the family of inequalities we propose, so to consider them in detail. So first I start with the formulation. So this is a formulation with an exponential number of variables. So here we have variables lambda for every feasible route and for every depot, because every route is attached to a depot. And so and then also we use a couple of more variables. So variables y, they are binary variables to decide whether we open depot I or not, and assignment variables z, whether we assign a client to a certain depot or not. And so our objective function will be to minimize the sum of the depot open cost and the routing costs. And the first constraint they are assignment constraints, that we need to assign every client to one depot. Second set of constraints, they link their route variables and the assignment variables. And third set of constraints are the depot capacity constraints. Means that if we can assign clients only if we open a depot, and if we open a depot, the total demand of assigned clients cannot exceed the capacity of this depot. And the last set of constraints is that less equal to y, so they are redundant constraints actually, so we don't really need them. Yeah, if you worked before with allocation problems, you would know that. So it's also important to read these constraints because they strengthen a lot the formulation. But we add this last set of constraints in a dynamic manner as cutting planes. And actually, here Z variables are not really needed, so we can take them out of the formulation and obtain equivalent formulation. But I prefer to keep these constraints for the clarity of the exposition. And so the family of inequalities we're going to present, they actually exploit quite a basic structure which appear in this problem. This is what we call nested knapsack structure, because here, so as a first level knapsack, we have a depot, and we need to assign to the depot set of routes. And each route has a size. The size of each route is a total demand of the clients assigned to this route, and we will call this total demand the load of the vehicle, which follow this route. And so the total load of the vehicles assigned to the depot cannot exceed the depot capacity. But there is also a second level knapsack here. It's when we assign clients to the route, to the vehicle. The demands of these clients, the total demand of these clients cannot exceed the capacity of the vehicle. And so we have here two level knapsack structure. So we have a capacity of the vehicles. We assign clients to the vehicles which have certain capacity, and then we assign the vehicles to the depots which also have a certain capacity. And so we have this. We can represent this constraint in the two equivalent ways. So either using the Z variables, assignment variables, or using the route variables, lambda variables. And so then we have these two knapsack constraints, and we can actually use standard knapsack inequalities for both of them. But we claim that the knapsack inequality is based on the second constraint, which uses lambda variables, and they would be stronger than the first. And so that's what we're going to do is to generate knapsack constraints for the constraints which are expressed with the lambda variables. And for that we will reuse results which are known in the literature for a quite long time. So we start with the definition of this master knapsack polytope. When we need to, so master knapsack polytope is the polytope which defined by all solutions to this master knapsack inequality. So we have here the variables for. So we have here a knapsack of the size W, and we have a variable for every value Q, which is from 1 to the size of this knapsack. And every variable is actually an integer variable. So each item can be taken as much time as needed. So here we needed to use this master knapsack polytope because as you remember, so in our case we need to so our knapsack is a depot, and our items are vehicles of a certain load. And actually, we can have several vehicles, several routes with the same load. So that's why we need to use here not only binary but also the integer variables. And so in quite a nice theorem which was proved by AIRO in '74. Is saying that every non-trivial facet of this master knapsack polytope can be described by inequality of this format xt less equal to 1, such that this vector xt is an extreme point of the following system of linear constraints. So here we have some normalization constraints xt1 equal to 0, xw equal to 1. Here we set of constraints is a complementarity constraint, and second set of constraint is a super additivity constraint. Okay, and so how we're going to use this result in our work is that as I say that we can have several routes with the same load, and we are going to use the variables theta, which actually the linear combination of variables lambda. The theta qi is the number of routes in assigned to depot I with the total load of exactly q units, and so we can have this theorem, which is not that difficult to show, that this inequality exceeded t less equal to 1 defines a non-trivial facet of the master knapsack polytope if and only if inequality exceeded theta less equal to yi defines a non-trivial facet of our knapsack constraint, of our depot capacity knapsack constraint. And so that we will introduce this family of road load knapsack cuts, RLKCs, which are the cuts which define it for a fixed depot and a fixed vector C, which satisfy these normalization constraints and also super additivity constraint. So the difference with the previous cuts to the previous facets of the master knapsack polytope, that the facets of the master knapsack polytope, they satisfy both super additivity and the complementarity constraints. And here we leave only super additivity constraints. Why we do that? Well, this is because to be able to use not only facet defining inequality, but also some other inequalities which are not facet defining, but still can be expressed in the same way. And so now the question, once we have these knapsack cuts, how we separate them? And the first way to separate them is actually quite standard. We can do it by Schwarzschild-Goldman rounding of this depot capacity constraint. This cut obtained by Schwarzschild-Goldman rounding is actually also a route load knapsack cut because the super additivity direct follows from the flow operator, from the rounding down operator. And so so we can separate that by Schwarzschild-Goldman rounding, and we can separate it quite easily just by enumeration of interesting multipliers. So we just look at the fractional solution in terms of the theta variables, and this fractional solution will give us all potentially interesting multipliers, because all other multipliers will be dominated. This cuts obtained by Schwarzschild-Goldman rounding, they are route load knapsack cuts, but they are not necessarily facets of the master knapsack polytope, because, as I said, they do not satisfy the complementarity constraints. And in order to really separate their facets, we will use this result by Chopra et al. And actually, they give an algorithm to separate not all facets, but very important subfamilies of facets, namely 1K facets. And what is 1K facet? Is actually the inequality, a master knapsack facet in which this coefficient C, they are all fractions with a denominator at most equal to K. Yeah, and so that's why these subfamilies of cases are important. So first of all, the Chopra et al. They showed also experimentally that most of the, many of the valid inequalities, they are 1K facets with small values of K. And also the small values of k will allow us to enumerate all these facets quite efficiently and find that the violated 1k facets also quite efficiently. And so we will use this also in our separation. So this is to give you a small example of comparison between the ROAD load knapsack cuts obtained by rounding and the facet defining 1k inequalities. Here I consider a small example with knapsack with a depot capacity 140 and the vehicle capacity 70. So this is the fractional solution. For example, here we see that there are the number of routes in the fractional solution with load 53 is 1/2. Yeah? And if we try to separate this fractional solution by rounding, so the best evaluated inequality we can obtain is the inequality generated with a multiplier 1/53, and which will give this inequality with violation 0.08. But a better facet defining 1/6 inequality can be obtained by the separation by Chopra et al. And the best violation here is 0.09. So it's not that much more, but still it's a noticeably larger violation. And so we can draw these two inequalities, and you can see that this 1/6 inequality it always dominates their the best Schwatel-Gomel rounding inequality for this particular fractional solution. And you see that why the violation is larger for the fractional solution, because if you take this fractional solution with load 38, so for this value Q38, the coefficient in the 1/6 inequality is 1/6, and coefficient of the Schwatel-Gomel rounding inequality is 0. So and this difference will give you the difference in the violation. Now it's good. So we can separate this ROAD load knapsack cuts, but these cuts are actually what we call a non-robust cuts. So because they can potentially change their the ROAD generation problem. So the way we solve the formulation, so the linear relaxation of the formulation is for a column generation algorithm, and in this algorithm we iteratively will generate a new ROAD variables. And the problem which generates new ROAD variables is called the pricing problem. And in order to efficiently solve this pricing problem, we will use a specific algorithm for the resource constraint shortest path, because the pricing problem here will be a resource constraint shortest path problem in the subgraph, which is generated by a certain depot I. And so how we solve this pricing problem? This pricing problem is solved by a labeling algorithm, which is essentially an enumeration algorithm, where every label represents a partial path from the depot, and so each label is characterized by the final node j, the current reduced cost of the partial path, and the current load of the partial path. And so this is an enumeration algorithm which potentially highly exponential. And in order to make it efficient in practice, we will use dominance relation, and we will discard non-promising labels. And the dominance relation, which is used for the standard vehicle routing problem, is the following. So the label L dominates label L prime if the corresponding partial path they end in the same node, and the reduced cost of the partial path L is less equal to reduced cost of L prime, and the load of L is also less equal to the load of L prime. So this is a valid dominance relation for the standard capacitated vehicle routing problem. But however, here the complete reduced cost of our path not only includes the dual values which correspond to the covering inequality constraints in the master, but else we need to take into account road load knapsack. And so what we will do, we will so this function mu bar will determine this contribution, and this function will still be non-decreasing and super additive because this as a sum of the monotone and super additive functions. And so super additivity comes from this with property of the facets, and the monotonicity is a special case of super additivity. And so we're going to use this super monotonicity and super additivity in the labeling, and why they will be useful for us. First, we can note that so as this function mu bar is non-decreasing, they are monotone. And this property allows us to prove that the dominance relation, which is used for the standard vehicle routing problem, is still valid for our case. So it's quite easy to show here. So you can see the last line. And what does this actually mean is that actually the labeling algorithm in principle does not change whether we have active route load knapsack cuts or not. So basically the pricing algorithm and the labeling algorithm, they are not changing in comparison to the capacitated vehicle routing problem. But actually this is not the end of the story, because in addition to the dominance rules, we use one more technique to speed up the pricing problem, the labeling algorithm, and this technique is completion bounds. So actually what we do not use just a monodirectional labeling, we use a bidirectional labeling in order to speed up the pricing, the solution of the pricing problem. And when we do bidirectional labeling, so we first extend the labels in the forward direction, then we extend the labels in the backward direction, and then we have this concatenation step to obtain the full paths. And this concatenation step can be quite expensive, and in order to speed up this concatenation step, in order not to try concatenation of every forward label with every backward label, we will use these completion bounds in order to take the whole bunch of backward labels and to verify whether a particular forward label is compatible with this whole bunch of backward labels. And if it's not compatible, it means that the bound which says that the least cost of the full path would be larger than the best path we have so far, then we can just keep the concatenation step with all this bunch of backward tables. And here, in short, the super additivity property of this function mu bar will allow us to have a tighter completion bounds, and so this tighter completion bounds will allow us to speed up more the concatenation step of the labeling algorithm. So this is what I wanted to talk about. So our contribution concerning this road load knapsack cuts. So we use a bunch of other inequalities, but I think that I will, due to the time, as I expected, I would not have time to present them all. So to present, but it's okay, because these are not original cuts. We just reuse the cuts which are known in the literature, and these are rounded capacity cuts. These are deeped capacity cuts, which are specialization of these rounded capacity cuts for the particular case with several capacitated deepets. These are cover inequalities for the deepets. These are weak knapsack cuts, so which are expressed in terms of the z variables. We can still add them and separate them. And these are eventual cuts over the y variables. These are also a type of knapsack cuts. This is actually to convexify the part of the polyhedron which concerns only y variables. So basically, this allows us to have strong inequalities over y variables, and they come from the inequality which says that the total capacity of the open depot should be greater or equal to than the total demand. So this can be reduced to another knapsack constraints, and we can add the from this knapsack constraints we can generate strong knapsack cuts, but this time only for the not for the clients but for the depots. And the last family of cuts is the Schwarzschild-Gomel-Rankman cuts, which are separated over their packing inequalities, which are relaxation of the partition constraints in the master problem. And these cuts are also non-robust, but so as I said, this is not new cuts, and we use these cuts. Actually, these cuts are already embedded to the VRP solver we use, and so. It's not. I think it's not that interesting to talk about them because they are already in the literature since 14 years already. And not only so as I said, we use this solver for vehicle routing problem, and this solver already embeds a lot of techniques which are known in the literature for the vehicle routing problems. So I will not explain them in detail, and also because I don't have enough time for that. So one thing I wanted to talk about more is about the branching, because branching here is more or less specific to the problem. And so we use the strong branching, and we use different branching decisions. For example, we can branch on the number of vehicles, we can branch on the total number of vehicles, on the assignments of clients to the depots, we can branch on the edges of the graph. So we have a lot of branching candidates. It's very important to use strong branching to find a good candidate. So there are a lot of branching candidates, and in order to among all these branching candidates, many of them will be not good. So it's important to find the best candidate to have the smallest possible branching price tree. And one more insight I can give here is that actually when we branch on the depot variable, so in principle we can branch on these y variables to branch on the decision whether we open this depot or not. Instead of that, we branch not on one depot, but we branch on the subset of depots. And computationally, we find that it's much better to branch on the subset of the depots instead of branching on the single depot. So you pick a subset of at most 4, and you branch on the decision how many depots in this subset are open. So this number is integer. That's why you can branch on this number. It's a kind of aggregated branching, and in many cases, the branching on the aggregated variables can be more efficient than branching on individual variables. So now I will pass to the computational results. So the first result I present is about the impact of the cuts on the solution times. So there is several lines here, but I want to pay attention to the 3 ones which are colored. So the first one in violet is actually these results. They correspond to the pure VRP solver results. It means that without any problem-specific cuts, only we include there only cuts which are generic for vehicle routing problems. And also you can see that this variant is quite less efficient than the other variants which use problem-specific cuts. And also we wanted to estimate the impact of our new family of cuts, the impact of route load knapsack cuts. But unfortunately, you can see here for these particular instances, which are classic in the literature for the location routing problem, the impact of route load knapsack cuts is quite small because it does not allow us to solve the more instances, does not allow us to decrease the solution time. The only thing it allows us to is to decrease the route gap. And we started to investigate this issue, and actually this issue can be explained on this by the fact that actually their capacity of depots in these instances is quite large in comparison to the capacity of the vehicles. And if you see this picture, in this case, the potential fractional solution, these black dots, will be situated very close to the zero in this x-axis, and if they're very close to the zero, the potential for cutting this fractional solution is very low. So this is the explanation we have why these cuts are not efficient for these particular instances, and also to confirm that hypothesis, we generated modified instances in which this ratio between the vehicle capacity and depot capacity is increased. It means that the relative vehicle capacity will be larger to the depot capacity. And once we start to increase the vehicle capacity in comparison to the depot capacity, the first thing we can notice that the instances become much harder. And another result we have is that our low knapsack cuts, they really make a difference, because if you take the instances with the largest raw ratio 0.7 is when the vehicle capacity is 70% of the depot capacity. You can see that the cuts, they allow us to greatly decrease the ROAD gap, practically divided by 2, divide by 4 the number of nodes in the branching price tree, and also the divide by 3 the total solution time, and will allow us to solve for more instances of the problem. And you can see also the statistics of cut generation here for these modified instances. We generate much more ROAD load knapsack cuts, and actually the cuts which are facet defining, they are generated much more than for the literature instances. And so some quick comparison with the literature. So we can solve much more instances than the best known approach so far. And another important remark here is that we started to solve instances which were never solved before, and these instances proposed by this heuristic paper by Schneider and Loeffler. So that's a way we can. So you can see that the solution time is quite high. So of course we cannot use this approach to solve large instances in practice. But what we can do, we can take the best heuristic and estimate whether this heuristic is good or not. And if you take this best heuristic in the literature, you can see that for the instances with up to this size, up to 15 depots and 300 clients, the improvement we get is quite low. So 0.2%. So means that up to this size, the heuristics are extremely good. But however, when we start to increase the size to the 20 depots and 300 customers, of course we cannot improve a lot of solutions. But when we improve solution, the average improvement is quite high. Is close to 1%. Means that the actual state-of-the-art heuristics for this particular size they are not extremely good. They are good, but they are not extremely good, and there is still a gap for improvement of this heuristics. And quickly about maybe one or two more related problems. So as I said here, so we artificially modified the instances. So you can say, okay, you artificially modified the instances so that your cuts will have more effect, but whether these instances are really practical or not. So because you can say that probably vehicle capacity, when vehicle capacity is close to the depot capacity, is not very realistic. But the thing is that this can be met in practice because this vehicle capacity, this depot capacity cannot really be the real capacity of the depot, but this depot capacity may come from this when the CLRP occurs as a sub-problem. So here in this work we did recently, we tried to solve this two echelon stochastic multi-periodic location routing problem, and their original problem, just one echelon location routing problem, appears as a sub-problem, which we also need to solve to optimality. And here the capacity of the depots, they are not like original capacities. This capacity of the depots, they come from the first echelon. This is the amount of goods which are brought to this depot from the upper level. And in this case, it's quite realistic to have the depot capacity quite close to the vehicle capacity. And you can see also here that impact of the ROD load knapsack cuts is quite noticeable here, and we can solve significantly larger number of instances in this case. And I also want to underline that these instances are quite small. It's 50 customers. If you take the standard multi-depot vehicle routing problem, this size of instances is solved very, very fast. But once we start to, in this case, impose the tight capacity on the depot, these instances, they become much, much harder. And even 50 customer instances, some of these instances cannot be solved even in 3-hour solution time. And so there is a potential direction for further research how to more efficiently solve these instances with a tight capacity. And the last related application is the VRP with time windows and shift. And here shifts are actually what we have here is that we have a certain time horizon, and the time horizon is divided into the shift, into the shifts. So there are different shifts of people working, and the capacity of vehicle charging is limited because of that. And actually, this problem can be reduced to our problem with capacitated depots. And we show that for instances of this problem, also our cuts will allow us to solve more instances to optimality. And so this brings me to the conclusions. So we introduced it. So the main methodological impact of this work is that we introduced a family of non-robust strong knapsack cuts for the problems with a nested knapsack structure, and we expect that there can be some other problems with a similar structure for which our work can be useful. And so these cuts are non-robust, and we needed to adapt these cuts to the pricing, and monotonicity and superadditivity properties of these cuts were quite useful for us to speed up the pricing time. And also this is the first exact algorithm for the original problem, which can scale to instances with many depot locations, because we do not have any explicit problem because of the number of depot locations. And recently, actually only this week, this paper has been accepted to the Operations Research Journal and subject to minor revision. And if unless some extreme events, so it will be published soon. So thank you for your attention.
Thank you, Ruslan, for the presentation. Once again, if you have questions, don't hesitate in the chat or by raising your hand. Just have a look to see if there is any hand raised. I don't see any. I was wondering, you mentioned the aggregated branching. Can you tell me how the group of variables on which you branch are selected? Is it random or?
Actually, yeah. Here it's quite simple. So we rely on strong branching. So basically, we define all possible branching candidates. So here we enumerate subset of size at most 4, and then we just try. Yeah, and we just try, and also we keep history of good branching. If some branching was successful, we will repeat it in other branches, and so it's a strong branching which does it more or less automatically.
Okay, so you enumerate all the possible set of size atmosphere and you try the strong branching on them. That's it?
Yeah.
Okay. And it doesn't take time to do this test because
of course it takes time. Yeah, we cannot actually we enumerate on them all, but we do not try them all. And this is a multi-phase strong branching, means that we start with just resolving the restricted master without any column generation, and then we select the best candidates, and then for these best candidates we do column generation and so on. So it's a gradual. So we start with something cheap with a lot of candidates, and we go further with something more expensive but with less and less candidates in order to select presumably the best one.
Okay, and is it a special case in which such branching works, or does it work on several types of column generation algorithm or non-column generation? Because I have not often heard about it.
Yes, it's. I think people just recently start to pay attention to that. So there was a recent work by the Martin Selversberg group about this type of branching, and recently Eduardo Shaw with his student considered what they call cluster branching for classic vehicle routing problems. Cluster branching is that they decided in advance the clusters of the clients, because usually in practice I think that the clients are distributed into the plane not randomly but more or less in clusters, and then they branch not on the individual arcs but on the aggregated arcs between clusters. And for some instances, this is really helps. Yeah.
Okay, cool. Thank you for the precision. Since it is time and I don't see any more questions, I think we will stop here. So thank you again, Ruslan, for the presentation.